Okay, welcome to the Chapter 8, Section 2, More About Recursion presentation lecture. We've already talked about recursion and how recursion is the form of a method that calls upon itself as a form of repetition. Up until this point, we have been working with loops, whiles, and now methods calling upon themselves, which is known as recursion. A second form of recursion is used when the solution to a problem depends on the ability to break a problem down into smaller parts and smaller sub-problems. Now we know that when we break problems down into smaller subsets, that is known as stepwise refinement. So how does recursion fit into a problem in which we use as a programmer stepwise refinement to solve the problem? Let's take a look at an example. All right, so we have the towers problem. This is one we are going to be doing together in class. This is kind of a game, and some of you might remember a game similar to this as you were growing up, maybe when you were younger. Now the challenge is to move all the disks from the source cone to the target cone. Okay, and so all of the cones are listed there on the slide. We are going to move one disk at a time. These are our parameters. These are our, I shouldn't say our parameters. These are our expectations and limitations as to how we can do this. We can only move one disk at a time. A larger disk may never be on top of a smaller disk. How are we going to handle this? All right, so we have the initial world, and these are the specs of the initial world. The disks are instances of the torus class. Torus class. A torus is an object, a donut-shaped object. Each cone is positioned exactly 1 meter from its nearest neighbor, and other than the bottom disk, each disk is positioned exactly 0.1 meter above the disk below. Okay, that's the initial world setup. That's our specs. That's what we have to work with. So let's identify the disks. To make it easier, we need to describe our solution. We need to give the disks labels so we can use them, or we can refer to them or call upon them in our methods. We give each disk an ID number and a name. So for example, disk number 1 is going to be ID number 1, disk number 2, ID number 2, and so on. Now, solving the problem, our solution will use the principle of wishful thinking. Now that might sound like, is this really something that a programmer would use? Wishful thinking is that we are going to assume that we could solve a smaller version of the same problem, and if we could solve the smaller version, it would make it easier to solve the big problem. So let's take a look at what base case is. Base case is the simplest possible version of this problem, one that can obviously be solved. Okay, so let's break this problem down so that we can solve the issue. Okay, wishful thinking in practice. Assume that I could move 3 of the disks to the spare cone, as shown in that illustration picture. Then I could move the 4th disk, or base case, to the target cone. Okay, and again, our end goal is to have all of the donuts on the target cone, with the largest cone being on the bottom, the smallest cone being on the top. All right, so let's take a look at our storyboard. To solve the towers problem, we need to know first how many disks we have and which cone is the source cone and the target cone and the spare. So one method is possibly going to be the towers method with 4 parameters: how many, source, target, and spare. So how many, the number of cones, source, one of the cones, target, another one of the cones, spare, another one of the cones. So if how many is equal to 1, we want to move it, that's the smallest disk, from the source cone to the target cone. If that turns out to be false, then do an order, call the towers, move how many, that's the towers method, so that's the recursion, this is the recursive call. Call the towers to move how many, 1 disk from the source to the spare, using the target as the spare. Okay, hopefully you're following along. If not, not a big deal. Try and follow along. Once we start putting it together in code, it'll make more sense. Then we are going to move it, which is the disk number equaling how many, the source to the target. Then we're going to call the towers again, another recursive call, to how many is 1. The disks are going to go from the spare to the target using the source as the spare. So it might be a little bit confusing as to exactly what happens here. We're going to be able to solve this problem. Let's go ahead and start working through it. Let's take a look and see what we got here. All right, so first we have to move a disk. The challenge in this animation is how to move a disk from one tower to the other. In the storyboard for the towers method, we assumed that we had a method named move it that would accomplish the task. However, we really didn't have the instructions, the recorded instructions as to what's going to go along with the move it method. So to write the move it method, we need to know, first of all, what are the parameters to send into our method, and then what steps need to occur, how high to raise the disk object, how far forward or back to move it. All right, so the move it storyboard for the move it method is going to be this. 3 parameters, which disk, from cone, to cone. So which disk is the disk ID number, from cone, source cone, to cone, target cone. The storyboard describing the steps is, here's the move it method, here's our 3 parameters. It's going to be a simple list of instructions within a do and order control structure. Lift the disk up, top of the from cone, move it forward or back to the location above the to cone, and then lower the disk down onto the cone. Okay. Let's take a look at the first version. All right, so I'll open up the world here. Once you see it in action, it might make more sense. All right, so here's version 1. Here is our 2 methods that we have, the move it and the towers. Here's the move it method that we are looking at here, which disk equals 1. And we can take a look at what's going to happen here. These are the instructions that go along with that method. All right, and then here's the towers method. Let's take a look at that. Which it's not. There you go, towers method. You can see this is very similar to the storyboard that we took a look at. Here's the recursive calls. Right here, towers called twice. Let's run it and see what happens. So there we go, mission accomplished. You see the solution, you see the code, you see the world play, and you see that it works properly. We'll do this in class and see if we can get it to work the same way. All right, back. All right, so the concept illustrated in this example, the base case is written as an if statement. If the base case is not true, then instructions are executed to move one step closer to the base case, and the method calls upon itself. Repeated self calls eventually work down to the base case, and the recursion ends. So in this case, we are using recursion, and because recursion is going to eventually end, we have essentially written a conditional loop, but we've used recursion to do that rather than using an actual loop statement or control structure. All right, a klutzy. Let's take a look at klutzy here a second. The move it method contains 3 sets of nested if statements. Disk ID number is used to determine which disk to move. We got move up, move over, and move down. Okay, those are the 3 movements that the disk is going to use. Code is somewhat klutzy. It's not considered. Would be not elegant. So how do we clean this up to make it an elegant code? We would use an expression. Okay, we notice that the distance each disk has to move up and then back down is 0.3 meters more than 0.1. ID number, which disk? So we could use is we could use an expression to compute the distance for the up and move down instructions. We can move the appropriate disk 0.3 plus 0.1 with times which disk. Now the problem with trying to use this nifty math expression is what we need to have the disk's name to write a move instruction. For example, disk 1 move up. It must be an object. It cannot be the ID number. So how do we do this? How do we handle this? Let's take a look at the demo for version 2. Open that one up. All right, so here's version 2. So now we use an expression, which cleans up the code quite nicely. Not as many lines and as many command lines that was needed in the previous version. And the solution is going to be the same. I'm going to speed up. You can see that it works exactly the same as the other one did. We just have a little bit cleaner code. Okay? So elegant code versus non-elegant code, you might get the same result, but it's not necessarily the best way to write the code. So in this example, condensing the program code to make it more elegant may lead to other problems. We have to realize that. We have to debug the code as normal. A conversion function is one that it has a parameter to receive an argument of one data type and return some equivalent value, possibly of a different data type. Now in this example, what we did is we wrote our own function to convert the disk ID number to I. All right, so we will work through this as an example in class, which will help you understand it hopefully a little bit better. If your mind is a little bit swimming right now, that's fine. Feel free to go back and review all of the slides and see if that helps. Also, before our next class period, if you haven't already done so, make sure that you read Chapter 8, Section 2, second form of recursion, and then even go through the tips and techniques for Chapter 8, which is camera and animation controls, could also help you as you go through your exercises for Chapter 8. And then at the conclusion, after we have completed the in-class example, you will be assigned your Chapter 8, Section 2 lab. Okay, this concludes the Chapter 8, Section 2 presentation lecture. I will see all of you in the next class period.